Now, in this talk, I'm going to go over some speculations of mine having to do with special relativity and quantum mechanics and how we might be able to deal with some issues that appear there. So, in small physics, we have the question of why is quantum mechanics weird? And I really want there to be one answer only, one that we could explain to other people. And my idea here is that if we think about a ball just moving in a straight line and we take a film of this thing and we end up with 100 frames of it, that I believe that if you take those 100 frames and you just watch it, that's classical physics. It's like one thing logically follows another. Now, what happens in quantum mechanics is that we have exactly the same 100 picture frames, okay? Because it's governed by exactly the same algebra. So there's not a choice about where the ball is, okay? But what happens in quantum mechanics is you get the whole collection of 100 frames, but you don't know what order they're in, okay? So what do you do with that situation? Well, one of the things you could do is you could take all 100 frames, put them all together at one time, shine a super bright light, and you could look at it. And it would be really blurry. You could kind of make out that it was kind of there. That is what I think the wave function is. And then if you say, I really just show me something, you would go and you could pick out one of them and you could look at it and it would be clear as day exactly where it was. And you could keep on doing this. And over time you go, oh, I kind of get it. You've got a system where the ball starts here and ends up there. You just don't know which thing you're going to see next. So that is my approach. Make it all very visual. And of course you have to then make it very mathematical by what do you mean by all this stuff. And so that at least is my hope, because I think that can be explained to people if you understood what I just said. How about fast physics? So how does nature say, no, you can't go any faster than the speed of light? And I think if you think about it as a speed, you're never going to be happy. And you're going to go, I'll try a little harder. I'll get there. Well, I think there is different than a speed. It's kind of like time's relationship to space. And for things that go the speed of light, time is space. Whatever that means, they're the same thing, okay? Whereas if you and I have mass, we can sit around and tell stories. We actually have much more time than we have space. We're not really movers and shakers. And I think that's what the fundamental difference is. Photons can't sit down and tell you a story. They just like go. They're about going. They're talking. You get one chance to interact with a photon, and that's it. And then they're off to the other side of the universe, and you can't catch them. That's too bad. So that's the kind of how that I think about, because if it's about time being space, then is time. If you don't answer yes to that, then if you say I actually can go into more depth about what I've done in my life, then you're never going to be able to get to that. You're never going to go to the speed of light. I don't know. Doesn't quite hang together, but at least that's the kind of area I think about. And then what about small and fast physics? Well, I've seen in many situations where, because I always work with quaternions, where time is always sitting next to space, that there are all kinds of equations where physicists go, well, this is what's really important, and I'll ignore everything else. And I think with nature, she never ignores anything else. She always accounts for absolutely everything. So you kind of have to have a discipline of never dropping well-formed terms. And it really doesn't work that way. Physics is hard, okay? So if people say this kernel leads to some really deep stuff, they focus on the kernel, and they don't focus on the crumbs that come along with it. For me, the example is when I was trying to figure out how to do electromagnetism using quaternions. And I got to this point where I calculated, oh, I've got a b squared minus e squared. Okay, that doesn't make you very happy, but it made me very, very happy because that goes into the machinery needed to come up with the Maxwell field equations. Okay, but it also comes out with something known as the Poynting vector, as like a bonus. Well, except that people don't consider it bonus. It's like, oh yeah, we don't really deal with it. We're going for max because max rocks the house. And I'm like, yeah, but it's tagging along. It's like you've got to deal with those at the same time that you deal with Maxwell, don't you? And it's not like we have a discussion about this. It's just like omission central. There's like, they're not going to say the Poynting vector doesn't exist. Of course it does. They just don't work with it because it's kind of not in the program of how people have always taught EM. EM is you get this b squared minus e squared, you put it in Euler-Lagrange, you get the source equations for Maxwell, and you're fine. And it's like, yeah, but they're there too. And this happens with all my quaternions expressions. Is I can say, oh yeah, that's the standard stuff, and here's the extra stuff. The extra stuff is well formed. I didn't do anything illegal. What I did was non-traditional because I've got these extra terms, and I think you should respect them as much as our historical tradition has paid attention to the other terms. Because and the little work I've done with the extra terms, oh, I think it gets ugly pretty fast. In other words, physicists are pretty justified in saying, I don't want to play with it. Oh, it's got some nasty properties. But too bad, people. Seriously, too bad. Because it's going to be a situation where the thing that you really like, because it's got some really nice properties, well, it'll go to 0, and then you go, then we have no handle on anything. Well, you got those extra terms. If you would have kept them, you could deal with gauge symmetry, maybe, okay? And believe me, that's a big maybe, because relativistic quantum field theory, hard to do. I can't do it so well. But to me, this is a possible handle on it, because it's just clear that it's there, it's clear that it's dropped, and anything dropped can come back to bite you. At least, that's what I think. All right. Thank you very much.